The next type of probability distribution we are going to be looking at is called the Poisson distribution. Now, the conditions for this is that Poisson is used when there's not really a fixed number of trials. Instead, we are counting the number of events that occur in a given amount of time or space. The average rate at which events occurred is the same at all times, and that is represented with this symbol lambda. The number of events that occur need to be independent. That's the other big thing. So again, we need to be independent. The average rate is the same. We're never overlapping, and it's usually over a short period of time. Now, the commands are very similar to what we studied with the binomial distribution, but this time it's Poisson, PDF, and CDF. And the way this is going to be entered is when it says lambda, it's actually going to be lambda times t, times the number of times that it occurs. So we got to be a little careful here. The number of hits on a website during a given time interval has a Poisson distribution of an average of 3 hits per minute. And X is the number of hits in a 2-minute period. So T is 2. And we want to find the probability that there are 5 hits during a 2-minute period. So this would be Poisson PDF. We find the probability that X is 5. Okay, so I'm going to go to the distribution menu. And a quick way to get there faster than going down is actually to go backwards. So lambda is going to be, we're going to be putting in 6. We're actually going to be putting those two in together. So 3 times 2. So it's the lambda times the time. And the X value is 5. And that gives me 0.1606. Now find the probability that there are less than 3 hits. So that's 0, 1, or 2. Well, I could put them in separately, or I can do less than or equal to 2. Because this less than does not include the 3. Well, if I do that, that's a CDF. So that's about 0.062. Now find the probability that there are more than 2 hits during the 2-minute period. So more than 2 would be 3, 4, 5, 6, and so on. So that's 1 minus the probability of having less than or equal to 2. Well, we already found that. So 1 minus 0.062 is 0.938. Now, if you're using the NumWorks app, we're going to go to this inference section. We're going to get a probability. Now, this time we have a Poisson. And it asked me first for my parameter. Now I forgot. Yes, it has to be the 6 because it's 3 during a 2 minute time period. 6. I'm sorry about that. That's actually lambda times t. And it starts off with a less than or equal to. If you can see that, I'll scroll in. But I can go over here and choose. The second option is between two values, greater than. The last one is an equals to. So equals to 5 gives me the same value. Less than or equal to 2. Less than or equal to is that one. And we got the same answer. Whoops, I didn't mean to go backwards. Okay. This one is nice that I can actually do it greater than. So more than 2 would be 3 or more. And that gives me 0.938, which is what we got there. The number of traffic accidents at a certain intersection follow Poisson distribution with 2 per year. And we're looking at a 4-year period. So when we're putting this in, we're going to be multiplying those two together for lambda. And I know that's very confusing, but we're first going to find the probability that they're exactly 7. So whichever calculator you're going to use, I'm going to go ahead and use this one. Equals to is a PDF. We're going to multiply the 2 times the 4, and we're finding the probability of being 7. That's 0.1396. Less than 4 would be less than or equal to 3. That's CDF. Less than or equal to 3. 0.042. More than 2 is going to be 1 minus the probability of being less than or equal to 2. So you can do this in one command if you want. 1 minus lambda is 8, less than or equal to 2, 0.986. Yeast cells are suspended in a liquid medium at a concentration of 4 particles per milliliter. In 2 milliliters, so T equals 2. So we're actually going to be plugging in 8 again. What is the probability that they're exactly 6 particles? That's a PDF. Lambda is going to be 2 times 4. I wish it would give us the option of putting in the time, but it doesn't. That's 0.122. Now, the mean for a Poisson distribution is that lambda times the t. Oh my gosh, so hard. Variance is, guess what? Lambda times the t. Oh no, it's not. Yes, it is. And standard deviation is just the square root of lambda times the t. Oh my gosh, it's so easy. Okay, so yeast cells are suspended in a liquid medium at a concentration of blah, blah, blah. My mean is 2 times 4. Variance is 2 times 4. Standard deviation is the square root of that. Oh my God. So hard. .828. Hard formulas. Now, the last thing I want to talk about is that we can actually use the Poisson distribution to also approximate a binomial distribution. In the previous section, we learned how to compute probabilities for a binomial distribution. When the number of trials n is large, these can be hard to compute even with technology. Sometimes it'll cause an overflow. So when n is large and p is small, in other words, if my tests are over 100 and my probability is pretty small, we can use a Poisson distribution. Now, the way we're going to do that is if that happens, we're going to compute the Poisson distribution with P in place of that lambda and N in place of time. So remember how in the calculator we're typing in lambda times time? Well, it's going to be P times N. It's actually going to be our mean. Okay. So a Nevada roulette wheel has 38 pockets labeled 0, 0, 0, and 1 through 36. If you bet on 0, 0, the probability that you will win is 1 out of 38. Assume you bet on 0, 0 for 200 spins. And my probability is 0.0263. And we want to know the probability that you win exactly 6 times. So I can do a Poisson PDF. Now, when it says lambda, that's actually going to be our lambda times time. So that's actually going to be 200 times 0.0263. And X is 6. So now type this in. And I guess I didn't show you could do this yet, 0.0263. That makes it easier. Oh, happens to be X equals 6 again. And it finds it really, really fast. If we had tried that with the binomial, sometimes it'll freeze up. So we only can do that again if our trials are over 100 and our probability is very, very low.